an engineer should also develop some level of intuition, right. So, for example, if we saw the previous slide, we developed the transient behavior voltages, right, the function of voltage as a function of time at two different points on the transmission line. It seems to have some kind of an asymptotic behavior, right. So, you can say that it is following that kind of a shape, right, very reminiscent of capacitors charging, right. So, even if you had done a simple circuit where people had asked you for an RC circuit, if I were to turn on the voltage, find out what is the voltage as a function of time, right. Disregarding this transmission line effect, even in circuit theory, if I were to put in an RC circuit and asked you find out what is the voltage across the resistor or the capacitor as a function of time for a step input, you would have probably gotten this kind of a shape, right, which is very reminiscent of this 1 minus e to the t by tau kind of a function shape, right. Now, what I will do is I will try to give you an intuition, right, as to why these shapes make sense, right. Is there something about these transmission lines that can give us some intuition quickly, right, without even having to get the exact numbers. Say for example, I am not too keen on getting this 32 milliamps or the 48 milliamps, but I just want to perhaps just look at or comment about the shape. How is it going to look like? So, for example, the current at B had an asymptotically growing behavior, whereas the current at A seems to have this sort of a overshoot and then sort of settling down, right, which is actually more reminiscent of an inductor, right. So, let us try to see if we can get some intuition as to why these shapes come about, right. So, when we looked at the transmission line, we came up with two voltage reflection coefficients, gamma L and gamma S, one for the load and one for the source respectively. And we can notice that if the sign of these two is the same, right. So, when the product of these two become positive, then we notice that the voltage has some kind of a exponential decay, right. Whereas, if gamma L and gamma S, the product of these two is negative, or the sign of gamma L and gamma S is opposite, right. We have not done this specifically. You can in fact tailor the example that we took and you can manipulate the resistances, right. So, we took a load resistance of 200 ohms, a source resistance of 100 ohms, both of which were larger than the characteristic impedance, right. So, if you were to say take the characteristic the load resistance to be less than the characteristic impedance, say 10 ohms at the output, you will notice that the sign of gamma L will change, right. And you can redo the exercise and you will notice that the signs will start to alternate, right, the way you are putting feedback at every stage, right, that the pulse goes back and forth. They will keep adding in opposite signs. So, it will kind of look like a decayed ringing, right. So, you can see an oscillatory behavior, but the amplitude of this oscillation is sort of dying down with time, right. So, the real question is, can we get some intuition, right? Why are we seeing these sort of behaviors, right? So, what I did was I just wanted to showcase three situations, right. So, this is the first situation where the characteristic impedance of the transmission line is lower than the resistance of both the source and the load, right. So, this is very much close to what we saw for the worked out example, right. So, this is a software called ADS from Keysight, where I can simply do the same experiment that we did in the problem solving, where I have a step voltage of 1 volt, right, and I basically have a very short rise time, almost instantaneous for all practical purposes, 1 femtosecond, that is 10 to the minus 15 seconds, right. And then I have a source resistance of 500 ohms and a load resistance of 500 ohms, which is about 10 times the characteristic impedance of the transmission line. And the delay of this transmission line is about 0.1 nanosecond, right. So then if I were to do a simple transient simulation, right, with the transmission line effects, I basically get the kind of figures that we basically got, right, by step by evaluating the reflection coefficients. A computer is able to generate this quite quickly for us, right. But nevertheless, we are seeing the same shape, right. Remember, we are after an intuition for these shapes. So, we will go back to trying to model the transmission line using LCs, right. So, an ideal transmission line, lossless transmission line, we said could be modeled as inductors and capacitors. Ideally, I would need a distributed model, but just to derive this intuition, what I am going to do is I am just going to look at say a situation where I only have one LC, right, network. So, I have my source, the transmission line begins here, and say one model for the transmission line. Right, I say I am taking a pi model, right, this is the pi model. What is L here? This is the total inductance, right. And if you can recall from last week, right. So, the total inductance was something that we could derive from the delay and the characteristic impedance, right. Similarly, the net capacitance, right. So, these L's and C's can be evaluated. If you give me just the total time delay and the characteristic impedance, I can give you the lumped capacitance values and the lumped inductor values. Not to say that the transmission line is best described this way, we are just doing this to get some intuition, right, to the various shapes, so that we know how a particular situation will actually reach steady state before even going to calculating the reflection coefficients and so on, right. So, this is RS and this is my RL, both of which are much larger than my characteristic impedance Z naught, right. So, let us take this particular example, right. So, we have 0.1 nano multiplied by 50 ohms, this would give me 5 nano henries, right. So, I have about 5 nano henries of net inductance, right? This is not the distributed inductance L anymore. Similarly, here we have 0.1 nano divided by 50, okay, turns out to be 2 picofarads, right. So, I have a net inductance of 5 nanohenry and a net capacitance of 2 picofarad. Now, really the question is of identifying certain time constants. So, remember that for an RC circuit, the net time constant, right, is RC, right, and the time constant for an RL circuit, right? Okay. I highly encourage you to go back to your simple RC circuits, right, and RL circuits, okay, and take a look at the time constants. Right. So, time constant is usually a very important circuit parameter, and for an RC circuit, the time constant is the product of the resistance, the net resistance and the net capacitance. Similarly, the time constant for an inductor, right, is L by R, right, the inductance divided by the resistance, net resistance. However, we don't quite have a situation where there's only one inductor and one resistor, or one capacitor and one resistor, but there are some shortcuts to kind of find out what is the net impedance or the net resistance seen by any inductor or capacitor. So, in this kind of situation, I can say that the time constant for charging the inductor L in this kind of a pi model is L divided by Rs plus RL. Okay. Because to this inductor, Rs and RL are in series, right. So, you can sort of open the capacitors and you can short the voltage supply or the voltage source, and what you end up seeing is that the resistors Rs and RL are in series to the inductor L. So, they just simply add up, and if I wanted to find the time constant for charging this inductor, right, you will essentially get a time constant that is L by Rs plus RL. Another convenient model for the transmission line is the T model, right. And if I wanted to look at the time constant to charge this capacitor C, right, I will essentially see that when I short the voltage, right, and I short the inductors as well, that Rs and RL are in parallel, right. So, the time constant is essentially C times Rs parallel RL, right. So, hopefully, if you have not seen this, maybe this is the first time that you are looking at these sort of simple tricks, right. So, an engineer needs to know some simple elegant ways in which he can estimate the time constants for a particular circuit, right, of combinations of various. This is not even going into hardcore circuit theory, where it is standing with RLs and Cs, right. I'm sure there are more tricks in the bag for a seasoned engineer in circuit engineering, with even active elements like transistors, right. He may be able to quickly find out what are the time constants. There's even exercises to find simple poles and zeros for circuits, right. But nevertheless, for this particular situation, I'm only trying to bring about feel or clarity in why the shapes of these transient behaviors the way they are. So, now if I were to evaluate these time constants, I notice that, so let us do that quickly. So, I have 5 nano Henry divided by the sum of these two resistances 1000 ohms. So, this is equal to 5 picosecond. Okay. So, the time constant to charge the inductor through these large resistances seems to be 5 picoseconds, right? Whereas the case of the capacitor, we have 2 pico, right? And then RS parallel RL, they are the same, so it is 1/2 the resistance of the load or the source, which is 250 ohms, which gives us about 500 picoseconds, right? So you can say that the tau for the capacitor to charge, right? So the time constant for the capacitor to charge in this scenario is much larger than the time constant for the inductor to charge, right? So you can say that L by Rs plus RL is much smaller than C times Rs parallel RL, right? So the transient behavior will be that dominated by the charging effect of the capacitor in the transmission line as opposed to the charging effect of the inductor, right? Which is why we notice that the shapes that we see, right, look like that of a RC circuit where the capacitor is charging. In fact, I can even neglect the inductor in this case and say that a crude or an approximate model can be one where I just replace the entire transmission line with just a single capacitor, right? This is just an approximate model for the transmission line, okay? So remember that this is just to try to give you a certain intuition, right? So when you go to a real world job and you start looking at transient behaviors and you will start seeing these generic step like shapes, right? And immediately you should be able to say, right, whether the load impedances or the source impedances when compared to the characteristic impedance of the transmission line, whether it's higher, lower, you should be able to start making certain comments, right? That the charging behavior of the transmission line is the dominant behavior for this particular scenario. So this is a very powerful tool or technique to kind of get some intuition, right? So this is the situation where the characteristic impedance is lower than both the source and the load resistance. Now we'll try to look at an opposite situation where the source and the load resistance are both lower than the characteristic impedance, right? Okay, so here the situation has changed only slightly. All I did was keep everything the same but change the source and the load resistances to 5 ohms instead of 500 ohms, right? So it is now 10 times smaller than the characteristic impedance. Now when I hit the transient simulation, you can notice that the input voltage and the output voltage actually have different behaviors, right? Both are asymptotic, but one seems to be rising and the other seems to be sort of overshooting and then tapering down, right? Let's see what happens. Remember, in both situations, since Rs and RL are the same, the voltage that is to be established at steady state at Vin and Vout, both in the prior example and this one, is going to be half the voltage at the source, right? So 1 volt was the step. So I expect to have half a volt at both the input and the output of the transmission line in both situations, right? Whereas the approach to the steady state value is different, right? So we saw the prior case where the characteristic impedance is lower than Rs and RL. In this particular case, we are showing an example where the characteristic impedance is higher than Rs and RL both, right? And we notice that there is a change in the behavior. Of course, you can go back to your TS, gamma S, gamma L, right, approximation. That will give you the accurate, in fact, that is how the simulator actually simulates this, right, but it's able to do it much faster than we are able to do, right. But as humans, we should grow the intuition as to why it looks like this, right. So an AI tool or a simulator cannot tell you why the voltage looks the way it looks, right. So that I would say that this knowledge that you're gaining in the last 2 slides are actually more critical, right, for engineers that you choose to become, right. Because the ability to actually estimate gamma S, gamma L, TS, and then doing this methodically and routinely is something a simulator is already able to do, right. Forget about AI. But to particularly know beforehand, even before building the simulator or building the actual circuit, if you can grow intuition on what you expect to see, then those are even more powerful, right. So in this case, what can we comment about the time constants? So similarly, when we have L by Rs plus RL, and we are comparing that to C times Rs parallel RL, right, this time it is 2 pico multiplied by 2.5 ohms, which is only about 5 picoseconds, whereas L by Rs plus RL is 5 nano divided by 10 ohms, which is about 500 pico, right. So this time the situation has reversed itself, right. So we notice that L by Rs plus RL is much larger than the capacitor charging or discharging time, right. So in this case, I can simply approximate the transmission line as merely an inductor, right. Right. And for an RL circuit, you know that the voltage actually undergoes an overshoot and has this kind of a behavior, right, where this is of the functional form right. So remember, this is still only an approximate, right, where I am simply just replacing the transmission line with a single lumped inductor, right, is only to grow an intuition into the observed transient behavior for the voltages, right. So one way you can sort of also picture in your mind is, remember that at steady state, when I have 1 volt, right, and I have Rs and RL together being about 10 ohms, so the steady state current in this situation is about 1 volt divided by 10 ohms, which is 100 milliamps, right. So there needs to be about 100 milliamps that needs to flow through this entire circuit, right, from the source to the load, almost instantaneously, right. But because this transmission line is we saw that long transmission lines can have significant flux, right. So the magnetic field lines that are cutting through the closed loop area, right, can be quite large for long lines. Right? We notice that for such large currents, right? So remember that the flux is proportional to the magnetic field intensity, which is proportional to the current that is flowing. So larger is the current that's flowing, greater is the magnetic field, and greater is the flux, right? And hence the impact of the inductance, right? So we notice that in this particular scenario, since the RS and RL are fairly small compared to Z0, we notice that there is a large amount of current that needs to be pumped through, right, from the source to the load. So the inductive behavior of the transmission line seems to be the dominant effect. Whereas in the previous scenario, we essentially had the situation where RS plus RL was 1 kilo ohm, right? So in that case, the steady state current is only about a milliamp, right? So there the capacitive behavior, right, seems to be more prominent, right? So having to charge the entire transmission line to half a volt was perhaps more time consuming, right? So charging of the capacitor. So this is the last of the three examples. So we saw a situation where RS and RL were both higher than Z0, a case where RS and RL were lower than Z0. This is a situation where RS is greater than Z0 but RL is lower, right? This is the situation where you will actually find that the product gamma S times gamma L will actually be negative, right? So the case of ringing. So in this case, we essentially want to see where the RL and C are. So this is very reminiscent of an RLC charging, right? So I need both the inductor and capacitor in this situation. I cannot quite take away, right, either a capacitor or an inductor. Remember, if I only had R and L or R and C, I will not have a ringing behavior. A ringing behavior is only akin to circuits where I have both an L and a C along with the R, right. So here if we take a look at, say, the pi model, right. So this time the only comment we can make in terms of comparing time constants is that of the time constant related with the load resistance and the source resistance, right. So this time the source resistance is only half an ohm, very small resistance, compared to the source resistance which is 500 ohms, right. So if I were to look at the independent time constants, right, what can we comment about? So we can say that C times RL by 2 is going to be much smaller than C times RS by 2, right, because RS and RL are different by a factor of 1000, right. So one is 500 ohms and another is only half an ohm. So I can perhaps only discard this capacitance, right, and what can I say is the approximate model is one where the input branch capacitance is maintained. Right. So what we end up having in the approximate model is a situation where we have both inductors and capacitors, right, where I cannot quite neglect one for the other, right, and I end up with an RLC circuit. and it is well known that an RLC circuit has ringing behavior, right? So hopefully these three situations, right, that I have portrayed, and this sort of an idea of estimating the time constants, right, using a simple lossless model for the transmission line using a lumped inductor and capacitor, is a useful exercise that you can run in your heads in actual situations, and maybe perhaps explain or even make comments regarding the source and load impedances, or perhaps the nature of the transmission line, and so on, right? So when you see transient behaviors that are akin to RC charging or RL charging or RLC ringing, that you immediately think of this kind of a scenario, so that you can simplify the situation and better get grips to where you need to make the adjustments, right?